Now let's talk about derivation of a multinomial logit model. First, I want to cover the latent variable approach to deriving the multinomial logit model. A Nobel laureate in economics, Daniel McFadden, wrote a paper in 1973, and he proposed a innovative way to derive the multinomial logit model. He set up this utility function. Okay? So here u is equal to s of x plus epsilon of x, where u is the utility function, s is the systematic component of the function, and represents the tastes of the population. Basically, s represents the factors or contains the factors that presumably researchers of nominal response variables already know. And there's this error term, epsilon. Epsilon is the stochastic random component of the function, representing some individual specific features that are not included in the measurement. Okay? And one makes the choice of m out of a set of alternative choices when its utility, its associated utility m is greater than all of its alternatives. Okay? And similarly, we can argue that the probability of y equal to m, that is, an individual chooses m, is equal to the probability when the utility of that choice is the greatest among the available set of choices. And if epsilon follows a type 1 extreme value distribution, then the probability of y making that choice, m, given x and beta, is equal to this ratio. Okay, and in the numerator is a natural exponential function of x and beta m, a vector of regression coefficients associated with choice m, and in the denominator is a sum of the natural exponential function. Okay? So this is just an individual probability. A probability of individual making a particular choice, m, out of available set of choices. Why we need to figure this out? Well, because we want to use maximal likelihood estimation. We want to express the likelihood, the quasi-probability of observing the data as a function of these individual probabilities. To be very precise, is product of these individual probabilities, assuming IID. It is identically independently distributed random variables. Right? Then, once the likelihood is expressed as a product of individual probabilities, we can take a log of that likelihood, right? Because product is a series of product is not that mathematically tractable. So taking a log turns a likelihood into a summation. Okay? In product of, taking log turns likelihood, which is a product of individual probabilities, into a summation, which is much easier to handle. Right? Next step is to apply maximal likelihood estimation and numerical methods to solve for the beta coefficients. Okay, so this is one approach, what is called latent variable approach. Another approach is called probability model approach. Well, the multinomial logit model can also be derived as a probability model as done by Henry Thiel. So here is kind of conceptual process. First, let y have m nominal outcomes, number 1 through m, and there's no numerical meaning whatsoever related to these m numbers. And the probability y equal to m, individual making that choice, is the probability of observing m given x. Then a probability model can be constructed as follows. First, let's assume the probability of making a choice of m is a function of x beta. For example, going to be exponential, natural exponential function of x beta, which turns x beta, which makes sure that x beta, or exponential of x beta, is in the positive range. Then we're going to make some manipulation, algebraic manipulation, so that that probability is bound between 0 and 1. We will get into that detail. And also, the regression coefficient vector, okay, that is making a choice of m, lowercase m, over this reference category m, capital letter M. Here it does not have to be the highest level, the last level. It could be, the reference category could be any of these m choices, capital letter M choices. And this vector can be decomposed into this elements, or can be expressed as this array of numbers. Right? It differs for each outcome m, and the slope of or the regression coefficient vector of capital letter M over M is 0. Is 0. Okay, so that's assumption just to satisfy the conditions we lay out. What kind of condition? Well, the sum of all individual probabilities is equal to 1, and each individual probability is bound between 0 and 1. So the beta for education on the probability of being a blue-collar worker is different than the beta for education on the probability of being a craft worker. So blue-collar and craft worker, they're different categories in the occupational set. Okay, so how to set up the relationship between each individual probability and x beta? Okay, so here is how we're going to do. Okay, so we say, well, the probability, the log of the odds of what kind of odds? That is making choice of 1, the first choice, as opposed to the last choice m, is equal to x beta 1 over m. So here, 1 over m denotes the odds comparison. Okay, and from this setup, okay, we can get the probability of y equal to 1 is equal to the probability of y equal to m, capital letter M, multiplied by natural exponential of x beta. Here, beta is associated with this particular odds comparison. That is the probability of y equal to 1 over the probability of y equal to capital letter M. Here you can try out the derivation. Right? So from here, we can get to this point. And how to do that? Well, we take natural exponential of these two, of both sides of this equation. And because natural log and natural exponential functions are inverse functions, so they cancel out. So on the left-hand side, what's retained is the probability, is the odds, right? What kind of odds? Well, the probability of y equal to 1 over the probability of y equal to capital letter M. And on the right-hand side, we have natural exponential of x beta 1 over capital letter M. Then we move the probability of y equal to M to the right-hand side. We get this equation. And similarly, we can get a second result, a very similar result, and etc. until we hit capital letter M minus 1 choice, right? And people might be interested in how about odds comparison of probability y equal to capital letter M over the probability y equal to capital letter M. Okay? When that happens, we know that what's in this log is 1, right? So log of 1 is 0, right? Log of 1 is 0. And if we take exponential both sides, okay, then the left-hand side, right? The left-hand side becomes what? Natural exponential of 1 is, 0 is 1, right? Okay? On the right-hand side, what's left is this term. Excuse me, is this term. Right? So it's 1 equal to the exponential of x beta m over n, right? Well, because this is 1, then log of 1 is 0. The exponential again of 0 is 1, okay? So this side is 1, right? This left-hand side is 1. The right-hand side, because we take exponential function of both sides, right? Right-hand side is this term, natural exponential of x beta, capital letter M over capital letter M, right? So how these two gonna hold? Well, x varies, right? X varies. So only possibility we will get is that beta M over M is 0. And that's exactly what we talk about when I cover kind of conceptual derivation using the probability approach. Okay, so you have to kind of memorize the results because we're going to move to the next slide. So next slide, since all the individual probabilities add up together is going to be 1 because all these choices, we assume they're mutually exclusive and exhaustive, okay? So the summation of individual probability is going to be 1, okay? Then how about the probability y equal to capital letter M? Well, it is 1 minus the summation of all the individual probabilities except the probability y equal to capital letter M, right? That's from here. Then we continue. Well, we retain this 1. What about this individual probabilities? In the last slide, we just talked about that, right? For each individual probability, it turns out to be equal to the probability y equal to capital letter M multiplied back by what? Natural exponential function of x beta lowercase m versus capital letter M. Okay. And from this equation, okay, from the previous equation, okay, we can arrive at our next result. That is, we can figure out what is the probability y equal to capital letter M, you know, because from this is equal to that. It turns out to be 1 over 1 plus the summation of natural exponential function of x beta m, okay, lowercase m versus capital letter M from m equal to 1 to capital letter M minus 1. And also we can get this solution. That is, how about the probability y equal to lowercase m except the last category, right? That is capital letter M. Turns out to be this result.